Thank you for the introduction and welcome everyone. So I'm Laszlo Kovacs from CMF Simulations, a Montreal-based company focusing on building real-time training simulators for construction equipment. And as such, today I will be talking about pile driving construction equipment used at sites. And this paper was written in collaboration with our academic partners from McGill, namely the group of Jozsef Kovecses, and we also collaborate with the university in many other aspects, including improving our solver and implementing new features in our main tool, which is Vertex Studio. In here, supposed to see, yeah, there is a short video showing the equipment as simulated in Vertex Studio. This is just an overview. It's a pretty complex multi-body system. Every single piece of this is modeled in detail and with high accuracy. And but we also need to be able to provide sufficient and useful training for operators is that we need to have a real-time soil simulation for the training so the student can interact with the environment, can interact with the ground and use the machine as intended. So we identified we need efficient physics-based models for this piling simulation, which is sufficiently accurate to provide a realistic training. So we were considering here in three different types of drill. So you can see here hydro hammer, displacement drill, and continuous flight auger. They all use the same drill machine, but the equipment which is attached to it, they are different. So obviously the hydro hammer, its big weight is hitting on the pile, which is forced into the ground by just impact. The displacement drill forcing the same kind of pile into the ground, but by means of linear and rotary motion. And the continuous flight auger is actually more closer to a regular drill. So we came up with a simplified, efficient framework to model the reaction forces which is transmitted from the environment to the simulated multi-body system. And I will not go into details, I will just really highlight the main ideas here. So the resistance of the ground was modeled using two main components. So the base resistance and the skin resistance. So the base resistance is obviously developing at the tip of the pile, which is being inserted into the ground. And for this one, we use Terzaghi's formula or other bearing capacity formulations. And this is so the force developed in this case is proportional to the depth, and there are many other factors to consider here, like shape factors, depth factors, which gives us different ultimate bearing capacities. So another important element of the resistance of the pile when we are inserting into the ground is the skin resistance. It's mainly coming from friction with the sides of the inserted pile, and this is proportional to the lateral pressure, which can be also calculated based on different theories. So in here, what we can see on the right-hand side, these diagrams, and please notice the logarithmic scale. So there are different theories to consider, for example, the base resistance, and they are very different, in terms of the response, the magnitude of the response. So we obviously have to provide some kind of tuning factors for this model to be efficiently used, but this is good for capturing the main characteristics. But what I was talking about so far, they are quasi-static models in our case. So we had to augment this with some dynamic considerations. One of these important elements was communicated to us by our client that we need to capture the fact that when the displacement drill is inserting the pile into the ground, it's being rotated to transfer some load from the cool down resistance of the pile into the rotary motion. So basically for this one, we decompose the force based on the pitch of the instantaneous pitch of the motion. So that way we divide the resistance force, the skin resistance force, into two parts. One of them will contribute to the resistance in the vertical direction, the other one is the resistance torque. And the other important element was that we had to increase the the resistance torque at the bottom of the inserted pile with speed. So this is a complex picture here. I just again, now, the picture is not very complex, but I don't want to go into details too much. In the formulation, we considered here a lumped parameter model composed of basically a slope and a bulk. The bulk is representing here the lumped parameter of the soil moving along the helix. So in case of soil augering, the slope is representing here the helix, and the bulk is the soil itself. And the main assumptions were that we have three motion regimes here: linear motion, augering, and corkscrewing. So the linear motion basically can be kind of covered by the previously showed techniques, and augering, we needed to come up with a new model. And the corkscrewing is just a dangerous operating regime, which we also simulate, but it's not covered by the model which I'm presenting right now. Here, the main assumption that the flights are not filled completely with soil, and for this, we also introduce a user-defined parameter which can consider the um, which is basically defining what's the uplift velocity of the soil. So based on this, it's possible to come up with a free-body diagram and for this, and we define we start with the soil skin resistance force, and based on that we can derive all the other forces. So for example, the vertical pull down force, how the auger is pulling down itself into the ground relative to the surrounding ground by friction. We have penetration resistance model, and of course an augering resistance torque. What is more important here, instead of going into more detail into the formulation, is that we validated this model. For the validation, we received data from IHC or client, and these are diagrams which were provided by the subject matter experts. These are not specific drill reports, they are simplified drill reports provided to us by the experts, so we can successfully validate our simulation against these which have distinct layers and well-defined transition, because in the training, what's really important is to capture the transition between layers and train the operator for these changes. And we also conducted DM simulation. I forgot to specifically, emphasize at the first page that we don't use DM because it's just too slow for real-time simulation, but still Vertex is capable of doing real-time, not real, simulating DEM. And we use the DEM simulation as shown here with some kind of roughly tuned soil parameters to validate the forces against the provided SME data. What you can see here is basically just the simulation of the first layer in this in the soil. This is a kind of limitation we have with the DM model in Vertex. But for the first layer of the simulation, we've successfully validated the data against the SME, the simulation result against the SME provided data, both for the continuous flight augering and displacement drill. We also compared the simulation results to the provided subject matter expert data. So here what you can see that the operator was attempting to match the reference data. The reference data here is the speed and RPM, so the vertical speed, the penetration speed of the auger, and the rotation speed of the auger. This is what the operator was trying to follow. And at the same time, the output here from the simulation is the resistance force and resistance torque. you can see that the transition between the layers were captured quite accurately, and the model was accurate enough for operate training. There were some discrepancies with the expected um, speeds from the operator, but the model is not that much dependent on the speed itself, so the forces were still matched quite well. So what you can see here on the next slide is the equipment model in Vertex Studio. The forces which I talked about earlier were realized through a constraint in the system. The constraint is just shown here by this cylinder, and it was also slightly relaxed to allow inclination relative to the ground. And here at the end, I have a video showing the equipment in action. I have to state that, so yeah, now the outriggers are deployed. You can also see that the leader base is also deployed, so it keeps the machine stable during the operation. And we start augering. So this operation normally, a piling operation normally takes around 30 minutes to hour or 2 hours even in some cases. So this is an illustration. Here I use the soil parameters which representative of mud, so very easy to penetrate to the ground. And even with that one, I had to speed it up to fit it into this slide. So, but it gives you an idea what is being done. Here, the auger is penetrating into the ground, and then just soon enough, I will start to retract it from the ground. I think you could see that there is an auger cleaner which is being closed, and that's responsible to remove the dirt from the helix as it is pulled up. So, as I said at the beginning, this is a complex simulation with many aspects to consider. So the whole machine is modeled in detail, and we have an analytical soil model to provide realism and speed for this real-time simulation. The developed model is good for operator training, but it was also working with PLC in the loop, and the validation was done against DEM data as well. So this developed simulator basically supports equipment design, control, and human in the loop use cases. So thank you for your attention.